Hey guys, it is Mr. Van Loo, and I'm here to go through the solutions to your homework with you. Okay, so this is for the, let's see here, yeah, this is for the 08.electricity PDF that you were assigned. This is an IGCSE physics textbook, and first you were asked to do page 171 and answer questions 1 through 6. So the first couple of questions are pretty straightforward, especially number 2. I expect we don't need to go through that. It should be a review from grade 9. However, let's take a look at number 1. So we have 2 negative charges, and we're asked to determine whether or not they repel or attract. Well, the basic rule here is that like charges repel and opposite charges attract. I have a hilarious video that I could show you sometime, but not now. Okay, so key point, opposites attract, likes repel. And if you know those 2 things, then you can always answer this question. Okay, so number 3, what makes copper a better electrical conductor than polythene? The basic answer is that copper has what are called delocalized electrons, and these can move freely through the structure of copper. And this is part of the nature of metallic bonding, to bring it around to chemistry. So you have these positive copper ions, and they're surrounded by these free electrons that can move around and conduct electricity. Okay, so number 4, why is it easy to charge up polythene by rubbing but not copper? So polythene is what we call an insulator. It does not have electrons that can freely move like a conductor does. So when you put an electron onto polythene, the electrons tend to kind of stay put. They will stay on the surface of the insulator, and they will also distribute themselves evenly across that surface, which is interesting. So then for number 5, we have carbon as our nonmetal that is a good conductor. And when we're talking about carbon as a conductor, we're usually talking about graphite, which is one of the more common allotropes of carbon. You don't need to know that word, but you can look it up if you like. 6a, so which ends up with more electrons than normal, the comb or the hair? Someone is combing their hair, and it's resulting in electrical charge. An experiment that you can do at home. With a comb or with a balloon if you prefer. So the negative charge means that the comb is picking up electrons. There we go. So for 6b, the hair has lost some electrons, leaving behind more positively charged protons than electrons. Importantly, the hair has not lost all of its electrons. It's just that now there is an imbalance in the positive and negative charge. And that's usually what's happening with a charged object. It's not that it's completely positive or completely negative. It's just there's an imbalance. And the balance is either positive or negative. Okay, so there we go. All right, let's move on to the next part of your assignment. You have 2 questions here. You were assigned, give an example of where electrostatic charge might be a hazard. This is going to be anywhere that a spark would ignite a fuel. So you can think a gas station or perhaps fueling up a jet, something like that, I think is the example in your text. There you go. So that's one example. You can also look up the Hindenburg crash to see another very dangerous example of electrostatic charge causing a disastrous results. Okay, B, how can the buildup of electrostatic charge be prevented? Usually we would use a process called earthing or grounding, where you connect the object that you do not want to get charged up to literally the ground. And there are various ways to do this, but usually it's a wire going to some sort of stake, a metal conductor that goes into the ground. And that is the best way to prevent charge buildup. Okay, number 2, how many microcoulombs are there in 1 coulomb? This is a fairly straightforward conversion question, and we've seen these before, so I'm going to move on. Quick note, this little thing here, the U-looking thing, is not a U. It is called a mu, and it means micro. So that's a microcoulomb. Okay. Next up, page 175. The diagram shows electric field lines around a charged metal sphere that is being suspended in air by magic, apparently. Okay, so we need to copy this diagram and draw the direction of the electric field on each line. I have just copied it and drawn arrows. There we go. Easy. The convention here is that positively charged objects have field lines pointed away from the object. A negatively charged object would have field lines pointed into the object. So, important point there. B, if a positive charge were placed at X, in which direction would it move? It is going to move away from the sphere because, like charges, repel. If a negative charge were placed there, then it would move toward the sphere because opposite charges attract. Okay, note that in either case, though, the path of our positive charge at X will follow a field line, okay, which is interesting. Okay, next. Convert these currents into amperes, convert these currents into milliamperes. This is kind of not that interesting, so you can just look at the answers here. Let me know if you disagree with my answers or anything else you see in here, and I will happily take a look. Because as you guys know, I've made some mistakes in my life. And you know what? Probably going to continue. So if you see one, let me know. I'll be happy to take a look at it. All right, number 3. Draw the circuit using the right circuit symbols. Here is the completed circuit. You are also asked to label the direction of conventional current and the direction of electron flow. So, conventional current is going to come from the positive battery terminal. Electron flow will come from the negative battery terminal. Conventional current is a bit of an odd thing. A lot of students don't like it. I will let you know that I don't actually like it because the electron flow is what is actually moving. Conventional current does not flow, which is pretty annoying. When we study electricity later on, and particularly study it as you move into diploma program physics, what you will learn is that the direction of the electric field through the conductor does follow the direction of conventional current. So that's one way that I kind of set it up to make students a little bit happier. But yeah, conventional current is kind of annoying. All right, C. What is the reading on the other ammeter? The ammeters are going to have the same reading. It's going to be 0.5 amps. Okay, so they're in the same loop. Note that circuit is a synonym for loop. Okay, so our ammeters are in the same loop, so they have the same current. Current is constant throughout this entire loop. So if we break the circuit, then to answer part D, both of our lamps are going to go out because the loop has been broken. And in order for our circuit to be complete and for charge to flow, it needs to be unbroken. 4A and for B, just some fairly straightforward calculations. We have seen the formula for charge before, expressed as a formula for current, where current is equal to charge divided by time. Well, we can rearrange that slightly to get this formula, and then we plug in the relevant values. This should be this should be a 3. Let me just make that a little more clear. There we go. All right, next page. Okay, here we're asked what unit each of these things is measured in. First, we have potential difference. Potential difference is measured in volts, as is EMF. Okay, both are measured in volts. C, charge is in coulombs. D, current is in amperes. E, energy is in joules. All of this should be review. Okay, so for number 2, what type of meter is meter X? Meter X is an ammeter. What type of meter is meter Y? Meter Y is what is called a voltmeter. You can find both of these on a multimeter, which we will be playing around with after you guys get back, probably. Okay, for C, what is the reading on meter Y? Well, in order to answer that question, we should look at what I'm going to introduce here. In any given loop, the sum of voltage should be 0, okay? And our starting voltage in this case will be 12 volts. And from that 12 volts, we're going to subtract the voltage of all the other components in the loop. Okay, so first we subtract the voltage from component A, which is 4 volts, and then we subtract the voltage from component Y, which we don't know, but we can very quickly solve for Y here. We'll find that Y is equal to 8 volts. If you want a fancy word for this, this is called Kirchhoff's law for voltage. I don't think it's mentioned in this way in your text, though. Okay, so next, potential difference. Let's see, how much potential energy does each Coulomb have as it leaves the battery? Okay, so the first thing we need to look at is the formula here for potential difference, which is given by energy per charge. Okay, we then rearrange that and solve the equation for energy, and we get energy is equal to charge times potential difference. And once we know this, we can then plug in our values. We are given 1 Coulomb as our charge, and we know from the diagram that our potential difference is 12 volts. So that means we will have 12 joules per Coulomb coming out of the battery. Okay. E, how much potential energy is lost by each Coulomb passing through bulb A? Well, we can see here that when we measure the voltage across A, we get 4 volts. Okay, so here again, we're given a charge, 1 Coulomb. So we use the same formula. The energy is equal to charge times the potential difference that we have measured for A. And we get 1 Coulomb times 4 volts, and that will give us 4 joules. Remember that 1 volt is a joule per Coulomb, okay, as suggested by this formula here. Okay. Right. So next, F. We are asked how much charge passes through A every second. Well, in order to answer that question, we need the current through the whole circuit, and we know that it's given by ammeter X. So we have 2 amps going through component A, a light bulb, and we're given the amount of time by the question, every 1 second. Okay, so we then multiply 2 amps by 1 second, and we get this charge, 2 coulombs. Okay, Next, how much energy is radiated from A every second? Well, in the first part, we calculate that bulb A loses 4 joules per Coulomb. And in the next part, we calculated that 2 coulombs pass through our component every second through our light bulb. Okay, so we then multiply 4 joules per coulomb times 2 coulombs per second, and that will give us 8 joules per second, and that's our answer. So we know that 8 joules per second are radiated by bulb A. And you might recognize this unit. It's a watt. And you might also recognize that we now have a new formula, a formula for power. Okay, so power in this case is equal to current times potential difference. Okay guys, there's your homework. Please let me know if you have any questions, or again, if you notice any mistakes. I'm usually in a bit of a rush when I do these, so I'm a human being and I make mistakes, and I will fix them if I do. So I'm going to share this document with you as well, so that you can look it over in your own time. Okay, have a great day guys. I'll see you later.